there is still a conversation taking place far beyond the familiar planets. One side of it is here on Earth, where large radio dishes wait beneath the turning sky. The other side is a spacecraft launched before many of the people now guiding it were born. Between them lies more than 15 billion miles of space. A command sent from Earth needs a little more than 23 hours to arrive. The reply, when Voyager 1 sends one, requires the same long passage home. Nearly 49 years after launch, Voyager 1 is still working. Its surviving instruments listen for plasma waves and measure magnetic fields in a region no other operating spacecraft has reached. The information is sparse, carried by a transmitter with very little power, but it is still information from beyond the heliosphere, the broad bubble shaped by the sun's particles and magnetic influence. That signal gives Voyager a presence in the human world. Engineers can still ask it to change a setting, warm a component, or conserve a little more electricity. They cannot touch the spacecraft, and they cannot see it through a telescope as a detailed machine. Yet the connection remains, stretched across almost a full day of light travel time. This is the final active season of a much longer story. Voyager 1 left Earth on September 5, 1977. Its first purpose was not to cross interstellar space. It was built to pass Jupiter and Saturn, return measurements and images, and complete a planetary mission within the lifetimes of the people who assembled it. It accomplished that work, continued outward, and in August of 2012 crossed the heliopause into interstellar space. Nothing about that original assignment required anyone to predict the spacecraft's condition a million years later, much less a billion. The mission belonged to a human scale of calendars, budgets, launch windows, and working careers. But the path chosen for Voyager carried it beyond the part of the solar system where return was possible. Once the planetary encounters were finished, gravity and motion opened a different future. The power aboard the spacecraft is diminishing. Its radioisotope generators produce less electricity each year, and instruments have been turned off one by one, so that a smaller set can remain alive. In April of 2026, another instrument was shut down, leaving 2 science instruments operating. Eventually, the available power will no longer support the conversation with Earth. That moment will be an ending for the mission, but not for the object. The dish-shaped antenna will remain, the long booms will remain, the metal body and the gold-plated record, fastened to its side, will continue along the same outward path, no longer reporting what surrounds them. Voyager will change from a working observatory into an artifact in motion, and motion does not require a signal. Long after the last radio pulse reaches Earth, the spacecraft will still possess velocity. The sun will continue moving around the Milky Way. Nearby stars will shift. The galaxy will age. Voyager will be carried through those changes without knowing any of them, following a route that becomes harder to predict with every passing century. The question then is not simply how long Voyager can operate. It is what becomes of a human-made object after the world that made it is no longer there. To follow that question, we will begin close to the present, while 2 instruments still work, and the radio link still crosses the distance between Earth and the spacecraft. From there, the scale will widen gradually, beyond the remaining years of the mission, beyond the future of the sun, and into a galaxy transformed by time. For now, Voyager 1 is not a relic. It is still answering. The path that carried Voyager beyond the planets began with a rare arrangement of worlds. During the late 1970s, Jupiter, Saturn, Uranus, and Neptune occupied positions that allowed a spacecraft to move from one giant planet to the next, gathering speed through carefully planned encounters with gravity. Such an alignment returns only after many human lifetimes. It offered a route through the outer solar system that no rocket of the era could have managed by propulsion alone. Voyager 1 was assigned the shorter branch of that opportunity. It would visit Jupiter, then Saturn, with special attention given to Titan, Saturn's largest moon. The spacecraft was not designed as a monument, and it was not built with a trillion-year future in mind. It was a working machine assembled from aluminum, cables, insulation, instruments, computers, thrusters, and a broad high-gain antenna. Its expected operational life was measured in years. The design came from an age when spacecraft computers held less memory than many ordinary household devices now use for a single photograph. Commands had to be compact. Systems had to survive radiation, cold, and long delays without constant help from Earth. Critical components were duplicated where possible. The machine needed to recognize trouble, switch to backup equipment, and place itself into a condition from which engineers might recover it many hours later. That caution became one of the reasons Voyager endured. On September 5, 1977, a Titan Centaur rocket lifted it from Cape Canaveral. Voyager 2 had launched 16 days earlier, but Voyager 1 followed a faster path. Before the year ended, it had overtaken its twin and was moving toward Jupiter. The spacecraft reached the Jovian system in early 1979. Its cameras returned, cloud bands folded into storms, a thin ring around Jupiter and moons that were not quiet spheres of rock and ice. Io revealed active volcanoes with plumes rising above its surface. Europa showed a bright shell crossed by long lines, a landscape that would later encourage questions about an ocean beneath the ice. The planet and its moons became places with weather, geology, and history, rather than distant lights. Jupiter also changed Voyager's path. As the spacecraft fell toward the planet, Jupiter's gravity accelerated it. Voyager passed through the system and departed with more speed relative to the Sun than it had carried on approach. The planet had given the machine a small share of its orbital motion. Nothing touched Voyager. No engine needed to provide the full increase. Gravity curved the trajectory and opened the road to Saturn. Voyager arrived there in November of 1980. Saturn filled its cameras with a ring system, divided into thousands of narrow structures. Moons moved through gaps, disturbed ring particles, and cast thin shadows across the planet. The encounter revealed a system shaped by resonance, collisions, shepherd moons, and gravity acting through distances both small and immense. Yet the most important destination for Voyager 1's future was Titan. Mission planners chose a close passage because Titan possessed a thick atmosphere, something unknown on any other moon at the time. Voyager's instruments could not see clearly through the orange haze, but they confirmed an atmosphere dominated by nitrogen and rich in organic chemistry. The flyby gave Titan priority over the possibility of sending Voyager 1 onward to Uranus and Neptune. That choice also bent the spacecraft away from the broad plane in which the planets travel. Saturn's gravity redirected Voyager northward, relative to the solar system. After Titan, there would be no additional planetary encounter. The spacecraft had completed its original path, and its new trajectory carried it toward open space. In that moment, the mission acquired a second life. The cameras eventually went dark to conserve power. Instruments designed for planetary encounters were shut down when their work was finished. Other systems remained useful because the space between the planets was not empty. Voyager could measure charged particles, plasma waves, cosmic rays, and magnetic fields. As the influence of the Sun gradually weakened around it, the spacecraft became less like a visiting observer and more like a moving boundary marker. Years passed. The Sun's wind continued streaming outward, carrying particles and magnetic fields into a bubble around the solar system. Voyager crossed regions no spacecraft had measured directly. It moved through the termination shock, where the solar wind slowed, then across the heliosheath, where solar and interstellar material pressed against one another. In August of 2012, the surrounding particle environment changed. Galactic cosmic rays increased. Particles associated with the Sun declined. Plasma measurements later confirmed that Voyager had crossed the heliopause. It had entered interstellar space, though it had not left the Sun's gravity in every formal sense. Far beyond the heliopause lies the distant Oort cloud, and the Sun's gravitational reach extends much farther than its solar wind. The boundary Voyager crossed was not the outer edge of everything belonging to the Sun. It was the edge of the Sun's particle-filled bubble. That distinction matters because boundaries in space are rarely walls. There was no visible line. No flash crossed the spacecraft. Nothing announced the transition. Voyager simply continued moving, while the character of the surrounding plasma changed. What had once been a prediction became a measurement carried home through radio. Attached to the spacecraft was another kind of boundary crossing. Beneath a protective cover, Voyager carried a 12-inch gold-plated copper record. Its grooves held natural sounds, spoken greetings, music and images encoded into an analog form. The cover included diagrams intended to explain how the record might be played, where the spacecraft came from, and when it had begun its journey. The record was not a navigation system. It would not guide Voyager toward a listener. Space is too large, and the spacecraft is too small for discovery to be likely. Its meaning lay partly in the act of sending it. For a brief moment in the history of one planet, people gathered sounds of surf, wind, animals, voices, tools, heartbeats, and music, then placed them aboard a machine leaving the solar neighborhood. They could not know who might encounter it. They could not know whether anyone ever would. The message did not promise arrival. It only accompanied the traveler. And as Voyager moved beyond the planets, the record became less a greeting aimed at a destination than a physical memory carried into time. The conversation with Voyager will not end in a single dramatic moment. There will be no final switch that clearly divides mission from silence. Power will continue to decline, a little at a time. Engineers will keep choosing which systems remain active and which can be allowed to rest. The spacecraft will speak less often, with fewer instruments, until the remaining electrical margin becomes too narrow to support another useful transmission. Voyager carries no solar panels. At its distance from the Sun, sunlight is far too weak to sustain the spacecraft. Its electricity comes from 3 radioisotope thermoelectric generators, devices that convert heat from the decay of plutonium-238 into electrical power. The process has no turbine and no moving machinery. Heat passes through thermocouples, and the temperature difference between their hot and cold sides produces a current. This arrangement was chosen because it could operate for decades without the mechanical wear that would limit an ordinary generator. But radioactive decay cannot be paused. The fuel produces less heat as the years pass, and the thermocouples themselves become less efficient. The total supply of electricity falls by several watts each year. That decline is small enough to seem manageable over a few months, but over decades it reshapes the entire mission. The spacecraft once supported cameras, heaters, scientific instruments, communications equipment, and computers at the same time. Now every watt must be assigned with care. A heater left on in one location may mean that another instrument cannot remain active. A system that once operated continuously may be used only when needed. The machine survives through subtraction. This long process has given engineers an unusual relationship with Voyager. They are not simply commanding a distant robot. They are caring for an aging object whose condition can be inferred only through faint radio signals. A change in electrical current, temperature, or timing may reveal that a component is struggling. A carefully designed command can ask the spacecraft to use equipment that has not been needed for decades. The distance makes every decision patient by necessity. A command travels outward for more than 23 hours. Mission controllers cannot immediately see whether it worked. They must wait for the instruction to arrive, then wait again for the response. A single exchange can occupy almost 2 full days, even when the spacecraft reacts exactly as expected. Voyager's transmitter uses about as much power as a small household light bulb. From more than 15 billion miles away, that signal spreads through space until only an extremely weak trace reaches Earth. Large antennas in the deep space network collect it from the background noise, and sensitive electronics recover information from a whisper that has crossed the outer solar system. The connection depends on alignment. Voyager's high-gain antenna must remain pointed toward Earth with remarkable precision. Small thrusters adjust the spacecraft's orientation, correcting motions that would slowly carry the narrow radio beam away from the planet. Each correction uses a little propellant and a little power. As long as the attitude control system functions, the old spacecraft can continue facing the place from which it came. After communication ends, that precision will no longer have a purpose. The radio may stop, because the transmitter can no longer be powered, because the antenna can no longer remain accurately aimed, or because several fading systems finally make recovery impossible. Whatever the immediate cause, Earth will receive a final signal without knowing at first that it is the last. The antennas will listen again. Engineers may send commands and search for a carrier tone. They may change frequencies, timing, and transmission strategies. For a while, silence will still be treated as a technical problem, because Voyager has recovered from problems before. Only later will the absence become permanent. By then, the spacecraft itself will already be continuing onward. Its motion does not depend on electricity. The engines that launched it are long gone, and its small thrusters have never been responsible for carrying it across interstellar space. Voyager moves because an object in motion remains in motion unless a force changes its path. Gravity will continue to shape that path. The Sun still exerts an influence at Voyager's distance, though the spacecraft is traveling fast enough to escape and will not return. The broader gravitational field of the Milky Way also acts upon it. Over very long periods, Voyager will follow a path around the galactic center, much as the Sun and nearby stars do. It will not travel in a perfectly straight line forever. A straight path is only a useful approximation across shorter distances. On galactic scales, gravity bends every journey. The spacecraft will also begin to lose its carefully maintained orientation. Without powered corrections, tiny forces will gradually change the direction it faces. Uneven heating, traces of escaping material, and the pressure of distant radiation may produce minute torques. None of them would be noticeable during a brief observation, but over centuries, they can add together. Voyager may begin to tumble. The motion would probably be very slow. Its antenna might turn toward the former position of Earth, then away from it, then toward empty regions of sky. The instrument booms and dish would rotate together around a center of mass that engineers once controlled with great accuracy. There is no danger in this tumbling. It does not cause the spacecraft to fall, and there is almost nothing nearby for it to strike. The change is only one of orientation. A machine once built around pointing, measuring, and communicating will become an object with no preferred direction. The surrounding environment is sparse but not empty. Voyager moves through interstellar gas containing isolated atoms and ions. There are grains of dust, magnetic fields, cosmic rays, and particles accelerated by distant stellar events. The density varies from one region to another, yet even denser interstellar clouds would feel almost like a vacuum compared with the atmosphere near Earth. There is no wind in the ordinary sense. No rain reaches the spacecraft. Oxygen and moisture are not present in concentrations that could corrode its metal as they would on the surface of a planet. Temperature also works differently in open space. There is no surrounding air to become cold and press against the spacecraft. Voyager loses heat by radiation, and it gains a little energy from starlight, cosmic background radiation, and the final warmth of its own power source. As that internal heat fades, the spacecraft will become colder, though its temperature will depend on which surfaces face distant sources of light. Materials respond to this environment in their own ways. Insulation can become brittle. Plastics and coatings may change under radiation. High-energy particles can displace atoms inside metal and glass. Dust, grains striking at interstellar speed can leave tiny pits. Over thousands of years, the effects remain scattered and small. Over much longer intervals, they accumulate. Yet there is no obvious process waiting to dismantle Voyager quickly. It is too small to attract much through gravity. It is too far from dense planetary environments to encounter atmospheres or rings. Space between the stars offers few collisions, and most of the matter Voyager meets will be individual particles passing through or striking a surface one at a time. The spacecraft will age without weather. Its appearance will slowly change, but not in the familiar way of abandoned machines on Earth. There will be no vines, sediment, flowing water, or shifting soil. There will be only radiation, occasional dust, and time. The gold-plated record will share this exposure. Its cover protects the grooves from direct impacts, and gold resists many forms of chemical change. The copper beneath it may remain recognizable for an immense period. The diagrams etched into the cover will continue to describe a home that is moving away from the positions recorded there. Some of those diagrams depend on pulsars, rapidly rotating neutron stars, whose pulses can act as cosmic reference points. Their spin rates change over time. In principle, a knowledgeable finder could compare the rates shown on the record with later measurements and estimate when Voyager began its journey. But the map was created for a universe in which those pulsars could still be recognized. Over very long spans, some will slow, change, or stop producing detectable pulses. The stars of the local neighborhood will move. The sun will travel around the galaxy. The record's map will gradually become less like a current address and more like an archaeological layer. Long before that happens, Voyager will pass through the first milestones of its silent journey. In roughly 40,000 years, it will move within about 1.5 light years of a small star known as Gliese 445. The distance is close only by galactic standards. It is far greater than the separation between Earth and the outer planets, and far too wide for the star to capture the spacecraft. There will be no planetary encounter like Jupiter or Saturn. Gliese 445 will brighten slightly in Voyager's sky as the two paths draw nearer, then fade as they separate. The spacecraft will not notice. Its cameras will be inactive, its instruments unpowered, and its antenna turning without intention. 40,000 years is longer than recorded human history many times over, but it is still an early moment in Voyager's future. By then, the continents on Earth will have shifted only slightly. Familiar constellations will be distorted, but many of their stars will still exist. The Sun will remain a stable main sequence star. The Milky Way will still have spiral arms, gas clouds, and bright regions where new stars are forming. Voyager will be older than any artifact now known, yet the universe around it will still resemble the one it left. Its true separation from home will not be measured only by distance. It will be measured by the fading of every system that once connected it to human time. No mission clock will remain active. No calendar will travel with it. Years, centuries, and millennia will pass without being counted aboard the spacecraft. The object will keep no record of its own duration. It will simply cross one region of the galaxy after another, carrying a message whose sender can no longer correct its course, renew its power, or call it back. And the longest part of Voyager's existence will begin after nobody is listening for an answer. The first world to disappear from Voyager's story will not be a distant star. It will be home. Earth will not vanish suddenly, and the change will not wait for the sun's final transformation. Long before the sun becomes a red giant, its increasing brightness will begin altering the conditions that make this planet familiar. The sun is a stable star, but stable does not mean unchanging. Deep in its core, hydrogen is being converted into helium. The growing helium-rich center becomes denser over time, and the surrounding layers must reach higher temperatures to maintain the balance between gravity pressing inward and energy pressing outward. As a result, the sun gradually becomes more luminous. The increase is slight across a human lifetime. No generation can notice it by watching daylight from one year to the next. Across hundreds of millions of years, however, the effect becomes large enough to reshape a planet. Earth's climate is controlled by more than sunlight alone. Clouds, oceans, atmospheric gases, ice, continents, and living organisms all influence how much heat is absorbed and how much escapes. These systems can adjust to gradual change, but their ability to compensate is not unlimited. As the sun brightens, more water will evaporate from the oceans. Water vapor is itself a greenhouse gas, so additional moisture in the atmosphere can trap more heat. Chemical weathering may remove carbon dioxide from the air, weakening another part of the greenhouse effect, but the long balance that has supported surface oceans will become increasingly difficult to maintain. The details depend on future atmospheric chemistry and planetary feedbacks that cannot be predicted precisely across such long intervals. The broader direction is clearer, somewhere around 1 billion years from now, perhaps earlier, or later depending on the model. Earth is expected to become a far more difficult place for complex surface life. The planet will remain in orbit. Its mountains may still rise. Tectonic plates may continue to move. Rain may fall in some regions for a time. Yet the relationships among sunlight, water, and atmosphere will no longer resemble the world beneath you now. Plants that depend on present levels of carbon dioxide may disappear first. Ecosystems will narrow. As conditions continue to warm, the oceans will begin a long retreat. Water molecules reaching the upper atmosphere can be broken apart by sunlight. Lightweight hydrogen can then escape into space, carrying part of Earth's water away permanently. This is not a boiling ocean in a single afternoon. It is a planetary transition spread over immense intervals. Coastlines withdraw. Inland seas vanish. The atmosphere changes composition. The water that once moved through clouds, rivers, ice sheets, soil, and living cells becomes less abundant until the surface can no longer sustain the cycles that define Earth today. Voyager will be elsewhere while this happens. By then, the spacecraft's exact location cannot be projected with confidence. Passing stars and the gravitational structure of the galaxy will gradually complicate its path. It may be many light years from the sun, moving through a region of space with no connection to the climate unfolding on Earth. No instrument aboard it will detect the loss of the oceans. Its antenna will no longer face home. The golden record will carry images of water, rain, shores, and living bodies through a galaxy where the planet shown in those images has become dry. Several billion years later, the sun will approach the end of its main sequence life. The lyster, hydrogen in the central core, will become depleted. Fusion will continue in a shell, surrounding the helium-rich center, causing the sun's outer layers to expand. Its surface will cool even as its total output rises, and the familiar white-yellow star will become a red giant. Mercury will be consumed. Venus will probably follow. Earth's fate is more complicated. As the sun loses mass, the gravitational hold on the planets will weaken, allowing their orbits to widen. That outward movement might seem to offer Earth an escape, but the expanded solar atmosphere will create drag, and tidal interactions can pull a nearby planet inward. Models differ in their details, but many indicate that Earth is likely to be engulfed before the red giant phase is complete. Even in scenarios where the planet avoids direct capture, nothing recognizable would remain on its surface. Its oceans and atmosphere would have disappeared long before. Rock would be heated, altered, and perhaps partially melted beneath the sun, filling a large portion of the sky. There may be no Earth left as a separate planet when the sun reaches its greatest size. And if a scorched remnant survives, it will not be the place recorded in Voyager's images. The red giant phase will not last nearly as long as the sun's earlier life. Stellar evolution moves more quickly once the stable hydrogen-burning core is gone. The sun will pass through episodes of expansion, contraction, and changing fusion as its internal structure adjusts for a time. Helium in the core will fuse into carbon and oxygen. Later, unstable pulses will loosen the outer layers. Gas once held inside the sun will move outward, enriched with material processed during the star's life. The departing gas may form a planetary nebula. Despite the name, this structure has nothing to do with planets being born. It is a widening shell of stellar material illuminated by the hot central remnant. From far away, it may resemble a glowing ring, a layered bubble, or an uneven cloud shaped by magnetic fields, rotation, and interactions within the escaping gas. The display will be brief by cosmic standard. Over tens of thousands of years, the nebula will expand and fade into surrounding space. The atoms that once moved through the sun will become part of the interstellar medium, joining material from other dying stars. At the center will remain a white dwarf. The sun is not massive enough to explode as a supernova. Its core will contract until matter is supported by the quantum behavior of electron. The result will contain a large fraction of the sun's remaining mass within a sphere, roughly comparable in size to Earth. It will be intensely hot at first, but it will produce no new energy through fusion. A white dwarf shines because it begins its existence with stored heat. That heat leaks away slowly into space. With no furnace renewing it, the remnant gradually dims. The planetary system around it will also be altered. The surviving outer planets will occupy wider orbits because the sun has lost a substantial portion of its mass. Jupiter and Saturn are expected to remain, though their moons and rings will have passed through unfamiliar conditions during the giant phases. For a limited interval, increased solar output may warm regions that are now frozen. Ice on distant moons could melt or vaporize near their surfaces. Materials that remain solid throughout the sun's main sequence lifetime may enter atmospheres or escape into space. This warming would not create a second Earth in any simple way. The radiation environment, timescale, chemistry, and rapidly changing brightness of the giant sun would make the conditions unstable. Any temporary liquid water would belong to a system already moving toward another form. When the white dwarf remains, the outer solar system will cool again. The planets that survive will circle a dim stellar ember. Their skies will no longer contain the sun as we know it. Reflected light will weaken, internal heat will become more important, and the spaces between worlds will grow colder. Passing stars may eventually disturb those orbits. The sun travels through a galaxy filled with other moving stars, and over trillions of years, some will pass close enough to exchange small gravitational influences with the surviving solar system. Repeated encounters can alter planetary paths. A planet may be pushed inward, thrown into a more elongated orbit, or removed from the system entirely. The process would not happen on a schedule that can be forecast in detail. It is statistical and chaotic, yet given enough time, the orderly arrangement inherited from the present solar system, is unlikely to remain unchanged forever. Jupiter may one day become a free-floating world. Saturn could follow another path through the galaxy. Smaller bodies in the distant comet cloud may be scattered much earlier, some falling toward the white dwarf and others leaving the system. The solar system will not end at one moment. It will loosen. First, the climate of Earth changes. Then the oceans disappear. The sun expands. Inner worlds are lost or transformed. Gas moves outward. A white dwarf remains. The surviving planets widen their orbits, and distant gravitational encounters slowly separate what is left. Voyager has already begun that separation. Unlike the planets, it is moving fast enough to escape the sun. The reduction in solar mass during the red giant phase will make little difference to its freedom. By the time the sun sheds its outer layers, the spacecraft will have spent billions of years following the larger gravitational currents of the Milky Way. No wave of heat from the red giant will reach Voyager with destructive force. Distance will have diluted the radiation until it becomes another small contribution to the light-crossing interstellar space. The spacecraft may receive photons from the death of its own star without any system capable of sensing them. For a short period, the expanding nebula could be visible from a nearby vantage point as a colored shell around a brilliant central core. Voyager will not turn to look. The record attached to its body will continue to display a diagram based on the hydrogen atom, a map built from pulsars, and instructions for recovering sounds from Earth. Those markings will not change when Earth becomes uninhabitable. They will not change when the sun expands. The message will remain fixed while its point of origin is transformed. From a resting place on Earth tonight, the sun may seem like the most dependable object in the sky. It rises through cloud, weather, season, and history. Every human life has unfolded within its light, and every generation has known some version of the same warm disk above the horizon. That dependability is real on the scale of a life. It is temporary on the scale Voyager is entering. The spacecraft does not need the sun to remain unchanged. It no longer draws meaningful power from sunlight, and it does not orbit close enough to be carried into the giant star. Its journey has become independent of the system that launched it. After the nebula fades, the white dwarf will continue cooling for longer than the sun spent as a bright main sequence star. At first, the remnant will glow white and hot. Later, it will become yellow, then orange, then redder and dimmer. The change will be so gradual that millions of years can pass with little visible difference. 1 trillion years from now, the former sun may still retain some warmth. It will be much fainter than it is today, but it will not yet have become a completely cold black dwarf. The cooling of a white dwarf can extend across intervals far beyond 1 trillion years, depending on its composition and the physics of matter under extreme density. There may be no planet nearby from which to see it. Earth will be absent or unrecognizable. The outer worlds may remain in expanded orbits, or gravitational encounters may have separated them from the remnant. The location once called the solar system will be a small arrangement of old bodies moving through a galaxy that has also changed. Voyager will not return to inspect what remains. Its trajectory leads away, and the galaxy offers no path that naturally circles back to Earth's former orbit, even if some distant gravitational interaction bent its course toward the region again. The probability of passing close to the white dwarf would be exceedingly small. The spacecraft carries no memory of distance traveled. It cannot compare the fading remnant with the star that rose over Cape Canaveral on the morning of its launch. It cannot distinguish between the disappearance of Earth and the ordinary passage of another billion years. Only the record preserves a physical connection. There are human voices on it, spoken when the oceans were full. and the Sun was midway through its stable life. There are pictures of landscapes formed by water, bodies built from Earth's chemistry, and creatures adapted to a world of air and sunlight. The record does not describe what happened afterward. It does not say that the shorelines withdrew, that the atmosphere changed, or that the star became a red giant. It contains only a sample of one brief planetary era, captured before the long transformation began. By the time the Sun is a cooling ember, that sample may be one of the few human objects not buried, melted, scattered, or drawn into the final changes of the solar system. Voyager will keep it beyond the reach of home's destruction. Not because the spacecraft can protect a planet, only because it has already left. The Sun's transformation will not be the only large change surrounding Voyager. Long before 1 trillion years have passed, the galaxy itself will begin to lose the shape we recognize. Today, the Milky Way appears as a barred spiral, a broad disk of stars, gas, dust, and dark matter rotating around a central region. The Sun lies far from that center, embedded in one of the smaller spiral features between larger arms. Voyager began its journey inside this moving structure, and even after leaving the solar system, it did not leave the galaxy. It became part of a much larger orbit. The spacecraft travels fast, compared with anything built for movement on Earth, but its speed is small beside the scale of the Milky Way. The Sun requires roughly a few 100 million years to complete one circuit around the galactic center. Voyager's path will be different from the Sun's, yet it will also curve under the combined gravity of the galaxy. From nearby, that curve would be impossible to see. Across a century, Voyager seems to move along a nearly straight line. Across millions of years, the small pull of the galaxy becomes important. Across hundreds of millions, its route belongs to the slow turning of the stellar disk and halo. The spacecraft is not a tiny planet in the ordinary sense. It has no atmosphere, no internal geology, and no star around which it travels directly. But in one limited way, the comparison helps. Like a free object inside the Milky Way, Voyager follows a galactic path shaped by gravity from matter spread across enormous distances. That path will not remain simple. Stars pass one another. Molecular clouds move through the disk. Large concentrations of dark matter contribute to the galaxy's gravitational field. Each influence is weak at Voyager's location, but over immense intervals, weak influences can redirect motion. A close stellar passage could bend the spacecraft's trajectory. A distant one could alter it by a much smaller amount. Most encounters would leave no dramatic sign. The spacecraft would not swing around a star as it once swung around Jupiter or Saturn. The distances would usually be far too great. Still, tiny changes accumulate. This is one reason exact predictions fade so quickly. We know Voyager's present position and velocity with remarkable care because its radio signal can still be measured. Once that signal ends, there will be no new observations to refine the path. Even a small uncertainty will spread outward over time. After a few thousand years, the predicted corridor will widen. After a few million, it will become a broad region. After billions, no responsible calculation can assign Voyager a precise set of coordinates. The physics remains familiar. The starting information simply cannot be perfect enough to trace one car-sized object through every future gravitational encounter. The galaxy through which it moves will also be changing. The Milky Way belongs to a small collection of galaxies called the Local Group. Its largest members are the Milky Way and Andromeda, with dozens of smaller galaxies moving around them. Gravity binds this group together, even while the wider universe expands. Andromeda is now separated from us by more than 2 million light years. Its motion has long made a future interaction with the Milky Way an important subject of study. Simulations show that the two galaxies may pass close, exchange stars, and reshape one another over several billion years. But a galactic future is not a single clockwork prediction. Small uncertainties in the sideways motion of Andromeda, along with the influence of other local group galaxies, can produce different outcomes. Some models lead to a direct merger. Others produce a wider first passage, followed by later encounters. The exact timing and geometry remain less certain than the broad fact that the galaxies share a gravitational neighborhood and will continue influencing one another. Whatever form the interaction takes, it will not resemble two solid objects colliding. A galaxy is mostly empty space. If the Milky Way and Andromeda pass through one another, their stars will weave between stars from the other galaxy. Direct stellar collisions will be rare because the gaps are so large. The greater effect will come from gravity acting on the galaxies as systems. Spiral arms may stretch, long streams of stars may be drawn outward, gas clouds may compress, creating new regions of star formations before the available gas is gradually consumed or heated. Central black holes may move through a changing gravitational landscape and, under some scenarios, eventually form a bound pair. The night sky from any surviving world would be transformed. Andromeda might expand across a large part of the sky before its stars mingled with those of the Milky Way. New bands of light could appear. Familiar constellations would already have dissolved through ordinary stellar motion. But the encounter would erase even the larger pattern of the galaxy as it is known today. Voyager would be inside this event, yet almost untouched by it locally. No wall of stars would sweep over the spacecraft. No visible edge of one galaxy would strike another. The nearest objects would still most likely be separated by light years. Voyager would continue moving through sparse gas and scattered dust, while the gravitational field around where it slowly changed. Its path could be reshaped without any single moment of impact. A region of the Milky Way that once followed a stable orbit might be pulled into a long tidal stream. Stars from the outer disk could be thrown into wider paths. Some might remain bound to the combined galaxy. Others could be sent into the space beyond it. Voyager might share one of those outcomes. If it remains in a region that stays gravitationally bound, it could continue circling the remnant of the merged system. Its orbit might become larger, more elongated, or tilted relative to the old galactic disk. One circuit could require hundreds of millions of years. If it is carried into a tidal tail, the spacecraft might spend a long interval far from the central concentration of stars before falling back. If an encounter gives it enough speed, it could be ejected. That possibility must remain a possibility, not a prediction. Voyager is too small, too distant, and too sensitive to accumulated uncertainty for anyone to know which future path it will take. We can describe families of outcomes, but not choose one with confidence. The difference between them is profound. A Voyager that remains bound would continue to pass through the outer regions of an aging galaxy. Even there, stars would be sparse, yet some faint light would remain. Long-lived red dwarfs would still burn. White dwarfs would cool. The spacecraft would move through a system with a center, an orbit, and a gravitational home. A Voyager that is ejected would enter intergalactic space. The transition might not be marked by any visible boundary. The density of stars would simply decline. The gravitational pull of the merged galaxy would weaken behind it. Ahead, there might be no nearby star for millions of light years. The spacecraft would still not move through perfect emptiness. A few particles would remain. Radiation would cross the void. Dark matter, if distributed through the region, as models suggest, would still offering any surface or light. But the familiar structure of a galaxy would be gone. There would be no spiral arm, no disk, no regular passage through regions of gas and stars. Voyager would travel between large islands of matter, perhaps never approaching another galaxy closely enough to be captured. From the spacecraft's point of view, there would be no difference. Its instruments would be inactive. Its antenna would turn through space. The golden record would remain attached beneath its cover. Whether it circled a merged galaxy or crossed space beyond it, the machine would follow the same local laws of motion. Only an outside observer could describe the change. Imagine, for a moment, a map large enough to hold the local group. The Milky Way and Andromeda would appear not as grand spirals, but as two bright concentrations within a much wider field. Smaller galaxies would trace their own paths nearby. Voyager would be too small to mark, a point below the scale of the map. As the clock advanced, the two major galaxies would distort. Their outer stars would lengthen into streams. Repeated gravitational encounters might blend them into a more rounded stellar system. The smaller galaxies would be absorbed, scattered, or left on altered orbits. Somewhere inside that shifting map, Voyager would continue. It would complete no maneuver. It would receive no correction. The same velocity inherited from its launch and planetary flybees would be redirected only by gravity. The machine's future would emerge from the movement of galaxies, not from any remaining intention aboard it. There is a human contrast hidden in that scale. For most of history, the Milky Way was known as a band across the night, a pale road, river, or path whose meaning changed from culture to culture. People used the sky to orient themselves on land and sea, finding direction from repeated patterns of stars. Voyager began as a machine of navigation too. Its trajectory was calculated through the positions of planets. Its antenna was held toward Earth. Its clocks, thrusters, and commands all depended on knowing where it was and where it needed to point. In the far future, that precision will be gone. The spacecraft will still move through the galaxy that once guided human eyes, but no navigator will be following its course. The star patterns engraved into memory on Earth will have dispersed. The galactic band itself may no longer exist in the same form. Navigation will have become motion without destination, and the galaxy will carry Voyager farther into a future that no map from Earth was made to contain. Beyond the changing shape of the galaxy, a larger separation will be taking place. The universe is expanding. Galaxies that are not gravitationally bound to the local group are already receding from us. On the largest scales, the distance between widely separated regions of space continues to grow, and observations indicate that this expansion is accelerating. The cause is described with the name dark energy. That name identifies an effect more clearly than it explains a substance. Measurements of distant supernovae, the cosmic microwave background, and the distribution of galaxies toward an expanding universe, whose recent growth has been speeding up. The simplest current models treat dark energy as a property of space itself, one that remains present as space expands. If this behavior continues, distant galaxies will not remain visible forever. Their light must cross an increasing distance to reach the local group. As the space between regions expands, the wavelengths of that light are stretched. Visible light shifts toward infrared, then toward longer radio wavelengths. The galaxies become fainter, redder, and harder to detect. Eventually, many will cross a cosmological event horizon. This does not mean they move through a physical wall. It means that light emitted after a certain time will never be able to reach an observer here. The distance between the regions will grow too rapidly for the signal to make progress across the expanding space. The galaxies will continue to exist. Their stars will orbit. Their black holes will remain. Their own local histories will unfold. But no new information from them will arrive in the part of the universe containing the former Milky Way. Over tens of billions of years, the observable sky from the merged local group will become increasingly isolated. Large clusters, now seen through telescopes, will fade. The long filaments of the cosmic web will disappear from view. Galaxies whose light currently reveals the early universe will be carried beyond detection. An observer in that distant era could study the stars and remnants of the local merged galaxy, but the wider universe would be difficult to reconstruct. Without access to distant galaxies, the evidence for cosmic expansion would be limited. The universe might appear smaller and more self-contained than it does today. Its visible contents could seem to consist of one aging collection of stars surrounded by an immense, unbroken dark. Voyager will be somewhere within that changing view. If it remains bound to the merged galaxy, it will move through the last visible island of stars available to any local observer. If it has been ejected, it may look back toward that island as it grows fainter with distance. In either case, the spacecraft will not know that the observable universe has narrowed. No active detector will measure the redshift of departing galaxies. No computer aboard will compare one century with another. The disappearance will occur around Voyager without entering the record it carries. The record preserves a universe filled with visible structure. Its images were chosen when humans could photograph spiral galaxies, nebulae, planets, and star fields. The civilization that made it knew that the Milky Way was one galaxy among many billions. That understanding depended on light arriving from distances far beyond the local group. In the far future, such light will no longer be available nearby. The golden record may carry evidence of a sky that cannot be observed, again from its region of space. While the wider universe fades from view, the stars within the local galaxy will also be changing. Star formation requires cold clouds of gas. Within those clouds, denser regions can collapse under gravity, fragmenting into protostars. Heat rises in their centers until nuclear fusion begins, and a new generation of stars enters the galaxy. The process has never been perfectly efficient. Some gas remains too warm or too diffuse to collapse. Some is blown outward by radiation, stellar winds, and supernova explosions. Some becomes locked inside. Long-lived stars, planets, white dwarfs, neutron stars, and black holes. Galaxies can receive fresh gas from their surroundings, but that supply is not endless. Mergers may compress existing material and trigger new bursts of star formation. The interaction between the Milky Way and Andromeda could produce such episodes if enough cold gas remains available. Those bursts will spend part of the remaining supply. As billions of years pass, less usable gas will remain. More matter will be stored in stellar remnants. Some gas will be heated and expelled into regions where it cannot easily return. New stars will continue to form, but at a declining rate. The bright blue stars will disappear first. They are massive, luminous, and short-lived. Their cores consume fuel rapidly, and many survive for only millions of years. In the present galaxy, their light marks regions where star formation has occurred recently. When new stellar nurseries become rare, those blue stars will no longer be replaced. The galaxy will lose much of its brilliant color. Supernovae from massive young stars will become uncommon. The clouds once illuminated by newborn suns will fade, disperse, or remain too thin to collapse. Sun-like stars will endure longer, but they too have limited lives. One by one, they will expand, shed their outer layers, and leave white dwarfs behind. The population of the galaxy will gradually shift away from active stars and toward remnants. The smallest red dwarfs will remain. These stars contain only a fraction of the sun's mass. Their interiors transport material efficiently, allowing them to use a larger share of their hydrogen. They release energy at a restrained rate and can continue shining for trillions of years. Some red dwarfs alive today may still be producing light when Voyager has traveled for 1 trillion years. Their appearance will differ from the stars most familiar in Earth's sky. They will be faint, cool, and reddish. A planet would need to orbit close to receive substantial warmth, and such worlds may face strong stellar activity during the early lives of their stars. Yet longevity belongs to these small suns. While massive stars spend their fuel in brief luminous lives, red dwarfs preserve it across intervals longer than the universe has existed so far. They will become the final common sources of starlight in an aging galaxy. At 1 trillion years, the universe will not be entirely dark. Some red dwarfs will still shine. White dwarfs will still release stored heat. Rare interactions may produce temporary light when remnants collide, capture material, or pass through unstable systems. But the sky will be poorer in bright stars than it is now. There will be fewer colors, fewer stellar nurseries, and fewer large clouds lit from within. Much of the galaxy's matter will reside in objects that produce little or no visible light. White dwarfs will be especially numerous. Each will contain the compressed core left by a low or medium mass star. Some will orbit one another. Others will travel alone. Their early heat will fade over spans far longer than the present age of the universe. After 1 trillion years, many will still be warmer than the space around them. They may glow in deep red or infrared wavelengths, too faint for unaided human vision at ordinary stellar distances. The former sun, if it remains gravitationally associated with the remnants of its planetary system, will be one member of this population. Neutron stars will also persist. They are the compressed cores of stars that ended in quark collapse. Many begin by rotating rapidly and producing beams of radiation. Over time, their rotation slows. Their detectable pulses weaken, and the pulsars used in Voyager's engraved map may no longer serve as recognizable beacons. The map will age with the galaxy. Its lines will still point toward numerical ratios, describing pulse periods as they were measured in the 1970s. But the objects represented by those numbers will have changed. Some will be inactive. Their positions will have shifted. A future finder would need to reconstruct a stellar past no longer visible in its original form. Black holes will remain as well. Stellar mass, black holes, will move among the old stars and remnants. The central black holes of the Milky Way and Andromeda may have merged. Depending on the history of their galactic encounter, the resulting object could contain millions of times the mass of the Sun and sit near the gravitational center of the combined system. At 1 trillion years, such black holes will not have disappeared through Hawking radiation. That process, if the present theory is correct, operates across timescales far greater than 1 trillion years for astrophysical black holes. They will still belong to a much later future. Voyager is unlikely to pass close to any of them. Even in a galaxy filled with remnants, the space between objects remains immense. A direct encounter with a star, planet, or black hole requires an alignment so narrow that the probability stays low. Most of the spacecraft's future will contain no encounters at all. There may be a red star somewhere across the distance. There may be a white dwarf, too faint to see without instruments. Gravity from the galaxy will continue bending Voyager's route, but the nearby environment will usually remain sparse. This absence of events is part of the scale. A trillion-year journey sounds as though it must contain an endless sequence of discoveries. For a silent object crossing interstellar space, the opposite is more likely. The duration is immense because so little interrupts the motion. Voyager will pass through regions where stars once formed. The clouds will be gone or changed. The massive stars will have ended. Their material may be locked in, remnants, or scattered too widely to gather again. The spacecraft will not distinguish a former nursery from any other part of space. Its metal surfaces will receive an occasional particle. Radiation will alter tiny portions of its material. Its slow tumble will continue. Each motion will take place beneath a sky with fewer sources of light. And beyond the last local stars, the galaxies that once filled the universe will already have slipped from view. By the time Voyager has crossed 1 trillion years of motion, the most difficult question may no longer be where it is. The harder question may be what remains. On Earth, machines are worn down by contact. Water reaches seams, oxygen reacts with metal, dust enters bearings. Heat expands one material while cold contracts another. Roots split pavement, sediment buries surfaces. Organisms settle into cracks, and weather repeats its work until even large structures lose their edges. Voyager left nearly all of those processes behind. Interstellar space contains no rain, no flowing water, and no atmosphere dense enough to produce ordinary corrosion. There is no ground beneath the spacecraft and no seasonal cycle around it. After its power source cools, its temperature will change only when it passes through different radiation environments or receives light from a nearby star. This does not mean perfect preservation. The galaxy is sparse, but particles still cross it. Cosmic rays travel at high energies and can pass into solid material, displacing atoms along their paths. Some are protons, others are the nuclei of heavier elements. A single changes very little, but Voyager will receive countless small strikes across immense intervals. Its metal will gradually accumulate, microscopic damage. Crystal structures can be disturbed, chemical bonds can break. Insulating materials may become brittle, surfaces may darken or change their ability to reflect heat. Components that once depended on exact electrical properties will lose those properties long before the main frame disappears. The electronics will not remain usable. Semiconductors are vulnerable to radiation damage, and electrical connections can degrade even in an environment without moisture. The magnetic patterns that once represented stored information may not survive. Capacitors, wiring, detectors, and computers will become a collection of altered materials, rather than a dormant system waiting to be restarted. No future engineer could simply provide power and expect Voyager to awake. The spacecraft may retain its outline, while losing every functional relationship that made it a spacecraft. Its broad antenna may still be attached. The central equipment bus may still hold together. Long booms could remain extended, though joints and thin components would be more vulnerable than the heavier body. Occasional dust grains will strike at high speed. Most will be very small. They may leave pits, melt tiny spots, or send fragments away from the surface. Larger impacts are possible, but the probability of meeting a large object remains low because the volume Voyager crosses is so nearly empty. Given enough time, even a rare event becomes less easy to dismiss. A collision with a substantial grain could puncture a thin panel. A larger fragment might break an instrument boom or tear part of the thermal blanket away. An encounter with a comet, asteroid, or planet would be far more destructive, but the chance of such an alignment is exceedingly small. Voyager does not need to survive without damage. It only needs to avoid complete destruction. This distinction matters because durability across 1 trillion years does not imply that the machine remains exactly as it left Earth. It suggests something more modest. Large portions of its structure may continue to exist, altered by radiation and impact, but still carrying enough of the original form to be recognized. The result would be closer to a fossil than a preserved instrument. A fossil does not keep every molecule from the living body that came before it. Its significance lies in continuity of form. It retains a pattern through change. Voyager may do the same. Atoms will be displaced, some will be lost. Others may arrive as dust and become embedded in the surface. Thin coatings may erode. The edges of the antenna could become uneven. Small components may separate and follow their own paths through space, yet the central body might remain. The gold-plated record may also endure, though its future is not guaranteed. Gold was chosen partly because it resists chemical change. The record's protective cover shields its grooves from direct exposure, and the copper beneath the plating provides a durable physical base, but radiation and impacts do not care whether a material was selected for symbolic reasons. The surface can still be damaged. A dust strike in the wrong place might scar the cover. Radiation could alter parts of the material. If the spacecraft tumbles for millions of years, every face will eventually turn toward different sources of light and particles. Even so, the record is small, compact, and protected. It may outlast the delicate instruments around it. The sounds stored in its grooves do not require functioning electronics aboard Voyager. They are physical variations in a surface. In principle, a finder with sufficient knowledge could recover them by examining the structure, even if the original cover instructions had become difficult to interpret. But finding the record is the least likely part of its future. Voyager is roughly the size of a small vehicle. Once its transmitter fails, it will emit no deliberate signal. Far from a star, it will reflect almost no light. Even a powerful telescope would need to be pointed toward the correct place and know what to search for. A passing civilization would not see it as a bright point crossing the sky. The spacecraft would most likely remain invisible until something came very close. The space available for such an encounter is immense. A galaxy can contain hundreds of billions of stars and still offer almost no chance that two small, unbound objects will approach one another. The same emptiness that protects Voyager from collisions also protects it from discovery. It may carry its record for 1 trillion years without any listener coming near it. That outcome would not change what the record is. The greetings, music, natural sounds, and images were selected during one moment in the history of Earth. Their existence does not depend on being received. They remain traces of intention fixed into matter and sent beyond the region where nearly every other human artifact will be erased. There is a generational thread within that act. The people who designed Voyager inherited astronomy from observers who had watched the planets without knowing they were worlds. They inherited mathematics from cultures separated by centuries and continents. They used radio engineering, metallurgy, nuclear physics, and celestial mechanics developed by generations who would never see the launch. Then they sent the result beyond their own lifetimes. The spacecraft became a place where knowledge from the past entered a future no human could witness. That future includes uncertainties deeper than ordinary navigation. At 1 trillion years, the basic laws used to describe Voyager's motion are still expected to apply. Gravity continues to shape its path. Atoms remain bound. Radiation continues to interact with matter. Beyond far greater intervals, some open questions in physics begin to matter. One of them is whether protons are perfectly stable. Protons form much of the matter in Voyager's metal, record, wiring, and insulation. Some theories predict that protons may eventually decay into lighter particles. No such decay has ever been observed, and experiments indicate that if it occurs, the lifetime must be enormously longer than the present age of the universe. 1 trillion years is still far too brief for the expected limits to threaten Voyager. Even if proton decay exists, its possible timescale lies so far beyond this episode's horizon that the spacecraft's atoms would remain secure through the entire period we are following. Other processes also belong to a later universe. Black holes may lose mass through Hawking radiation, but stellar and supermassive black holes require timescales far beyond 1 trillion years to evaporate. White dwarfs have not yet cooled into their final dark state. The last red dwarfs may still be shining. Voyager's trillion-year future remains within a universe that still contains structure. There are stars, remnants, gravity, radiation, and motion. The spacecraft may be damaged, but it is not yet being dissolved by the ultimate aging of matter itself. This leaves a narrow but meaningful conclusion. Voyager is not permanent. Nothing in current physics allows us to promise that. A random collision could destroy it. Radiation may weaken its materials more than expected. Galactic events could place it in an environment no model can foresee. The exact condition of the golden record after such an interval cannot be tested in advance. But complete erasure is not the most likely outcome we can describe. The more likely picture is partial survival, a darkened body, a damaged antenna, booms bent or missing, surfaces altered by particles that crossed the galaxy long after Earth had vanished. Beneath one side, perhaps, a metal disc still carrying patterns made by hands in the 20th century. The object would no longer be operational. It would no longer be clean. It might not resemble the museum images through which people once remembered it. Yet something of Voyager could continue to move, and in the long interval after function has ended, form alone may be enough. 1 trillion years does not lead Voyager to a destination. There is no final star waiting at the end of its course, no boundary where the spacecraft arrives and its motion becomes complete. The journey continues because motion itself does not require an arrival. This is where ordinary language begins to struggle. Human journeys are usually described by beginnings and endings. A ship crosses an ocean. A traveler reaches a city. A probe arrives at a planet, performs its observations, and sends the results home. Voyager completed that kind of journey long ago. The path beyond Saturn has no comparable endpoint. It is better understood as a changing relationship between one small object and the gravitational landscape around it. At any moment, the spacecraft has a position and a velocity. Together, those values describe not only where it is, but how it is moving through the universe. Gravity alters that motion continuously, even when no nearby object appears to be pulling on it. The Sun once dominated Voyager's path. Farther out, the gravity of the galaxy becomes the larger influence. If the spacecraft remains bound to the merged system formed from the local group's major galaxies, its route will curve through that system for as long as the system can retain it. A single galactic orbit may require hundreds of millions of years. Across 1 trillion years, Voyager might complete thousands of such circuits, rather than only a few. The exact number would depend on the size and shape of its future orbit, which cannot be known. A tighter path would carry it around the center more often. A wide, elongated path would take longer, but even thousands of orbits would not make its journey repetitive. The galaxy itself would change during every circuit. Stars would move. Remnants would exchange energy through distant gravitational encounters. Smaller systems would be absorbed. Some objects would be pushed inward, while others wandered outward. Voyager would never return to precisely the same place. There is no fixed background against which the spacecraft can repeat a path. Space is filled with moving matter, and time changes the arrangement through which every object travels. If Voyager is ejected, the geometry becomes simpler in one sense and lonelier in another. Its path through intergalactic space would be influenced by the diminishing pull of the galaxy behind it and by the remote gravity of structures elsewhere. It might travel for billions of years without passing close to a star. From a distance, its motion could appear nearly straight, yet even there, the universe would not provide a permanent coordinate grid. Space would continue expanding on large scales. Distant structures would recede. The meaning of location would remain relational, defined by whatever matter and light still occupied the surrounding universe. This is why no map can show where Voyager will be after 1 trillion years. The problem is not only that the future is long, the problem is that the path is sensitive to influences too small to measure perfectly now. A star passing several light years away can alter a trajectory by a tiny amount. Another encounter millions of years later acts on the path produced by the first. Each change affects the geometry of every change that follows. the uncertainty grows. This does not mean the laws of motion become unreliable. It means that accurate laws cannot produce an exact answer without exact starting conditions and complete knowledge of every future influence. Neither is available. The same limitation appears in weather prediction, planetary dynamics, and the motion of stars inside dense systems. Small differences become larger with time. Across 1 trillion years, even a measurement of Voyager's present velocity made with great precision is not precise enough. Science can describe the range. Voyager may remain bound to an aging galactic remnant. It may be carried into a wide halo orbit. It may be ejected into the space between galaxies. It may experience a rare encounter that changes its path in a way no present model can identify. What science cannot provide is a final address. There is a certain honesty in that absence. The future of Voyager is not made less meaningful because it cannot be plotted to the last mile. The uncertainty is part of the physical story. It reveals the difference between understanding laws and possessing complete knowledge. You can know why an object moves without knowing exactly where every movement will lead. The people who launched Voyager worked within that same distinction. They knew the equations governing the planetary flybys. They could calculate when the spacecraft would reach Jupiter and Saturn with great accuracy. They could aim instruments toward moons that appeared as points of light from Earth. Beyond the planned mission, certainty widened into possibility. The farther Voyager traveled, the more its future belonged to timescales for which the spacecraft had never been designed as an active machine. The mission plan ended, but the laws that carried it onward did not. That difference separates purpose from consequence. Voyager was built to study planets. Its survival into deep time is a consequence of where that purpose sent it. The Golden Record followed the same pattern. It was prepared as a message, yet it was sent along a path with almost no expectation of being found. Its creators understood that the gesture might never result in an encounter. A message can exist without a recipient. The grooves remain grooves even when no needle touches them. The images remain encoded even when no eye reconstructs them. The greetings remain physical patterns even when no listener hears the voices. Meaning began on Earth. It does not need to be completed elsewhere. This may be one reason Voyager continues to occupy such a distinct place in human thought. It combines precise engineering with an outcome beyond control. Every screw, wire, and instrument was chosen for a practical reason. Yet the object as a whole entered a future no engineering team could manage. It became both machine and accident, both mission and relic, both a measured trajectory and an unknowable destination. From the room where you are resting now, the distance to Voyager is already difficult to hold in the mind. A radio signal crosses it in almost a day. The spacecraft has been traveling since before the first personal computers became common in homes, and still, this distance is almost nothing compared with what lies ahead. The age of the universe today is about 13.8 billion years, but 1 trillion years is more than 70 times that span. Imagine the entire history of the cosmos so far placed into a single book. The first stars, the formation of galaxies, the birth of the sun, the rise of life, and every human century would all fit inside its completed pages. Voyager's trillion-year future would require more than 70 additional volumes of equal length. The spacecraft's launch would appear near the final line of the first volume. Everything that follows would extend beyond the history the universe has yet lived. Across that duration, the distinction between ancient and recent changes completely. 1 million years becomes a narrow interval. 1 billion years becomes one step in a much longer sequence. Even the death of the sun belongs near the beginning. The merging of galaxies belongs near the beginning. The fading of distant galaxies from view belongs near the beginning. Voyager continues after all of them, carrying a record of a world that existed during the earliest portion of its journey. The record does not contain a complete portrait of humanity. No object could. It holds selected sounds, selected images, and selected pieces of music. It reflects decisions made by a small group of people during a particular period on one planet. Yet, limitation does not make it empty. A single photograph does not contain an entire life, but it still contains light from a real moment. A short recording does not preserve a whole culture, but it still carries the movement of breath, language, and instruments through air. Voyager carries fragments. Fragments may be all that endurance allows. The same is true of the spacecraft itself. After 1 trillion years, it may survive only in part. Its structure may be marked, its thin components damaged, its surfaces changed. It will not carry the 1970s forward untouched. It will carry continuity. Some portion of matter, assembled near Earth, will still be moving because of decisions made by people who lived beneath the sun. The trajectory will be different from anything they could calculate, but the motion will remain connected to the launch. Cause can persist after memory disappears. A gravitational flyby at Jupiter can shape a path billions of years later. A choice made in a laboratory can determine which materials remain after every laboratory is gone. This is not permanence in the absolute sense. It is persistence through change. There is no requirement that Voyager remain forever for its future to be immense. 1 trillion years is already enough to separate it from nearly every condition under which it was created. By then, the spacecraft will not belong to Earth in any physical way. Earth may no longer exist. The sun will be a fading remnant. The stars used to describe Voyager's departure direction will have moved beyond recognition. Only history would connect the object to its origin, and history may survive nowhere except in the object itself. Still, the connection is real. Voyager's metal was refined from material found on Earth. Its record was touched by human hands. Its motion began with a launch from a coastline beneath an atmosphere filled with weather. For one brief interval, it was surrounded by voices. Commands entered its computers. Radio signals returned. Engineers watched numbers appear on screens and learned what waited around distant planets. Then the voices faded. The screens went dark. The planet changed, and the object continued, carrying the physical result of that brief conversation into a universe where no conversation lasts forever. Somewhere beyond the last familiar shape of the solar system, Voyager 1 is moving through a region no human being will ever visit. There is no boundary ahead that will complete its journey. The spacecraft will pass through changing fields of gravity, cross regions of thinner and denser interstellar matter, and continue beneath skies that become less recognizable with every age. The stars will rearrange themselves. The sun will fade from a star into a remnant. The galaxy will lose its spiral form, and the wider universe will recede beyond observation. Voyager will not witness these changes. To witness something requires memory. It requires a way to compare what is present with what came before. Once its remaining systems are silent, the spacecraft will hold no active record of the distance it has crossed or the errors that have passed around it. It will not know when Earth becomes uninhabitable. It will not know when the oceans are gone. It will not know when the sun expands, when the inner planets are transformed, or when the remaining solar system settles around a white dwarf. The spacecraft will continue before, during, and after each event, with no change in purpose, because purpose will no longer be operating aboard it. There will only be matter and motion. The antenna, once aligned with Earth, will turn through space. The instruments that studied Jupiter, Saturn, and the edge of the heliosphere will remain inactive. The small thrusters will no longer correct the spacecraft's orientation. Yet the trajectory will remain connected to everything that came before. The launch from Florida is still part of that motion. So is Jupiter's gravity. So is the encounter with Saturn and the decision to pass close to Titan. Each event altered the path that followed. Even after 1 trillion years, Voyager's position will be one consequence of choices made during a few years in the 20th century. The connection will be physical rather than remembered. A spacecraft does not need to understand its origin for its origin to remain part of it. The direction of travel, the distribution of mass, the shape of the antenna, and the record attached to the body all carry evidence of an earlier world. That evidence will become harder to interpret as the universe changes. The pulsars engraved on the record's cover will age. Their periods will shift. Some will stop producing detectable signals. The stars around the sun's former neighborhood will move into different arrangements. A map that once pointed toward Earth will become a map of a vanished sky. Its markings may still be readable, but the reader would need to reconstruct a past galaxy from clues preserved on the object. The record would no longer function as a simple address. It would be an archaeological problem written in metal. The images stored within it would present another challenge. They show bodies shaped by gravity and biology, water flowing across a planetary surface, tools made by hands, food, landscapes, mathematics, and the structure of the solar system as it was understood at the time of launch. To any future finder, these images would describe a place that may no longer exist. There would be no living Earth available for comparison. The sun might be too faint to identify without careful reconstruction. The surrounding stars would no longer occupy the positions shown in the diagrams. The message would speak entirely from the past without a surviving world nearby to confirm it. Perhaps no one will ever find it. That remains the most likely outcome. Voyager is small, dark, and unpowered. It may spend its entire future crossing space without passing close to another inhabited system, another spacecraft, or any detector capable of recognizing it. The record may never be played. The greetings may never be heard. The photographs may never be reconstructed. Still, they were sent. For a brief period, one species had enough knowledge to understand that the stars were distant suns, enough engineering to reach beyond the outer planets, and enough imagination to place sounds of its world aboard the departing machine. The gesture was not based on probability. It was made in the presence of uncertainty. That uncertainty remains part of Voyager's future. We cannot know whether it will stay bound to the merged galaxy or enter intergalactic space. We cannot know which surfaces will survive radiation and impacts, or whether the record will remain recoverable after 1 trillion years. We cannot give the spacecraft a final location. We can only follow the range allowed by physics. Within that range, Voyager continues after communication ends. It survives the transformation of the sun. It moves through the reshaping of the local group. It enters an era when small red stars dominate the remaining light and distant galaxies have disappeared from view. Its form changes slowly. Dust leaves marks. Radiation alters materials. Thin components may break away. The spacecraft becomes less complete, less functional, and more difficult to recognize. But no single instant needs to erase it. Its future can be a gradual passage from machine to relic, and from relic to an arrangement of old material still following the momentum of its departure. There is no triumph in this process. Voyager does not defeat time. It does not remain untouched, and it does not preserve humanity in full. A record cannot contain every language, every life, every landscape, or every way people understood themselves. It carries fragments, a few voices, a few images, a small selection of music. The pulse of a heart recorded during one narrow period in the life of a planet. Those fragments are enough to show that something once listened, measured, built, and sent. For now, the connection has not ended. Radio antennas on Earth still turn toward Voyager's position. Engineers still work with systems assembled decades ago. Signals still cross the distance, carrying information from the spacecraft and commands from the planet that launched it. The exchange is fragile. It depends on dwindling electrical power, aging components, precise pointing, and receivers sensitive enough to separate Voyager's transmission from the background of space. One day, the final signal will arrive. It may contain science data, engineering information, or only a simple carrier tone. At first, no one will know with certainty that nothing more will follow. The dishes will continue listening. Commands may be sent. Time will pass while the distance is crossed in both directions. Then the mission will enter history, while the object itself continues beyond it. Earth will still turn for a while beneath the same sun. Seasons will continue. Human voices will fill rooms, streets, and radio channels. The spacecraft will be remembered in photographs, archives, and models. Much later, even those records may disappear. The planet will change, and the star will change with it. Voyager will move farther from every place where its name was known. At 1 trillion years, there may be no remaining context for calling it a spacecraft. There may only be an object of metal and glass crossing a dim region of an old universe, but the motion will still carry the shape of its beginning. A launch, a sequence of planetary encounters, a final radio conversation stretched across the edge of the solar wind. Then silence, followed by time. The record turns with the spacecraft beneath the last red stars.